Welcome back all of you to second session of Algae Nexus conference. Second session will start with Ralf Steuer instead of Lars Bahar. It's needed to switch between their time of presentation. We will first welcome Ralf Steuer from Humboldt-University of Berlin by the title of Fast-Growing Phototrophic Microorganisms and the Productivity of Phototrophic Cultures. Your stage is yours.
Okay, so let's start. So thank you very much. I want to thank also the organizers for organizing this, in particular in the face of the terrible news we had. Okay, here. So in my talk will be about fast-growing phototrophic microorganisms. And I don't think I need to convince you that phototrophic microorganisms, so microalgae, cyanobacteria, have many amazing applications in green biotechnology, and we already heard quite a few. Victor gave an extensive talk about all the applications, and there are many ideas. So I also started on this topic. Oh, should I talk louder? Everything good? I started so in the context of biofuel production mostly, but the field has now diversified. There's a huge variety of potential products and applications you can do, from biocatalysts, wastewater treatment, we already heard, aquaculture is an important topic. We have animal feed and food, but there are still some dark clouds over algae town, and in particular the yields and the productivity you typically get out of algae and cyanobacteria are not yet there what you would expect for heterotrophic bacteria. So the overall productivities and the overall yields are still something that need to be improved to have an actual application that is sustainable in economics. So there are several ideas how to maximize phototrophic productivity, and I will quickly step through some of them. One that has been proposed many years already ago is antenna size truncation, and the idea is that a shellfish cell in evolution would absorb light to the best of its interest, and usually will operate at a high light intensity, would operate at a low quantum efficiency. So what would be desirable is a more like socialist culture where everything gets, every cell gets a little bit. So you decrease the absorption of the individual cell and get a higher quantum efficiency per cell, have a higher culture density, and in this way improve the productivity of the culture, allegedly. So this has been proposed many years ago. I think now the Melis is one of the person who has developed this also in the experimental applications. A second way to improve productivity is, in particular for cyanobacteria, has become quite prominent over the past years, is to look for fast-growing strains. So typically we work with the usual lab strains, and these are good, and there are many good reasons actually to stick with them, as we already heard. But people are now specifically looking for fast-growing strains, and for cyanobacteria, there have been now a number identified with division times 2 hours or less. Also for algae, so you have this Chlorella ohadi, which goes much faster than a conventional Chlamydomonas. And it's very interesting scientifically, of course, to understand why are these strains growing fast. But in the context I will talk about, I want to highlight they are also motivated as a way to overcome productivity barriers. So that's one of the motivations to look at them. And what I want to discuss now is basically the problems with both of these approaches. First, the antenna size truncation, and also the fast-growing strains, starting with the fast-growing strains. And I will take the perspective from modeling. So my usual job is to construct metabolic models of phototrophic organisms, and usually we have these very large models with hundreds of reactions. But what I want to show here is the simplest possible model that you can imagine. That's phenomenological growth equation like this here. So all of you have very likely seen Monod equation. Jacques Monod suggested this as a phenomenological equation that describes growth of a bacterium. So you have here the growth rate or the division per hour. Here you have the glucose concentration. You have this hyperbolic growth curve, and that describes growth rate as a independence of the nutrient, this equation here. It's phenomenological, so it's not a mechanistic model. And just for those who specifically work on modeling these kind of organisms, I want to mention that the Monod equation is not the best to describe growth of algae or cyanobacteria because it fails to describe the decrease here at high light intensity, so photoinhibition. I will ignore this for the moment. I will just say all simulations are actually done using a slightly different equation. So there's a whole zoo of these kind of phenomenological growth equations that incorporates this. In the explanation, I will stick to Monod simply because it's more simple and it doesn't make a difference for anything I say. So you all know this equation, that's the Monod equation. And the question is now, how do these parameters we have here relate to things like productivity and yield? And for this, I want to reformulate this equation. And I'm aware that many of you specifically come to these conferences to hear about equations and mathematics, but I will still try. And what I want to emphasize is that this is the same equation. So I'm not using a different equation. I just reformulate it. So what I do here is I introduce this k here. I do the k here. They cancel. So it's still exactly the same equation. Then I introduce this alpha here, and I introduce the alpha here. So they again cancel. They don't change the equation. And this alpha is the extinction coefficient and has the units of square meter per gram dry weight, or here, gram dry, cellular dry mass. I will consider monochromatic light. So in principle, you would have to now make this more general and have this wavelength specific, but for the sake of the argument, we just consider one wavelength, then it's a single number, and it's related to optical density, so you absorb light. Now we have this equation here, and it's the same as the Monod equation. We can again write it down, so that's the one we have. And like I said, it is still the Monod equation. If you plot it, you exactly get the same curve, but now we have these three factors. And these three factors have meaning, so that's why we can now discuss the Monod equation in terms of its properties with respect to yield, productivity, and so on. And to quickly go through them, the first term here is the rate of light uptake. So this is the extinction coefficient multiplied by the light intensity. This, if you multiply them, has units of mole photons per gram cellular dry mass per time. That's the amount of photons you absorb per gram dry weight. Next term is the quantum efficiency. Where is it here? Quantum efficiency or quantum yield has no dimension, so it's a yield. And it measures how much of these photons that you have absorbed actually go into a productive process for growth. So it's a number between 0 and 1. And importantly, it's a decreasing function of light intensity. So the higher the light, the lower your quantum efficiency. Also, it's a decreasing function of growth rate because the growth rate increases with light intensity. So at higher growth rates, you will have a lower quantum efficiency. The final factor here is the maximal biomass yield per photon. So if you look at the units here, it will give you gram cellular dry mass per mole photons. And that gives you how much of these photons that are now used productively are actually converted into biomass. And for this, we can get numbers either from these genome scale models I showed in the beginning. So you get about 1.8 gram cellular dry mass per mole photons. This is for growth on nitrate. For cyanobacterium, if you use ammonia, you get a bit more because it uses less electrons. It changes slightly with the composition. You can also calculate it from the overall stoichiometric equation, so how much nitrogen, what is the source of nitrogen, and it gives you similar numbers. So we have a good idea about this maximal rate. So the first take-home message is that light-limited growth is a product of these three factors. It's the rate of light absorption, so how many photons do you absorb per gram dry weight? It's the efficiency with which you can process these photons, and then how much biomass do you get per time per photon. And I like this because it's not apparent to everyone that this is part of the Monod equation, so it's all in there basically. And the message is now that first, high maximal growth rate itself is not a sufficient measure to judge productivity. So what we would need to know is which of these factors is increased. So is it the maximal yield that is higher? That would be very good. Is the quantum efficiency better? That would be very good. The rate of light absorption, if this is higher, I mean, then they grow faster, but they are not more efficient. They just consume more light. And I had this very nice car here in the beginning. This is a fast growing car, so to speak, or fast driving car. But it's not an efficient car. It won't increase your productivity, depending on your occupation, of course, but usually it's not considered to be a productive car. And the reason is that it drives fast, but it also consumes quite a lot of fuel, and actually consumes more fuel proportionally to the increase in speed. So the question is, for the cyanobacteria and algae, what do they do? I unfortunately don't have the full data, but there are indications that these fast-growing strains are actually more high light adapted or high light tolerant strains. So this is a plot from the book of Paul Hudson here. They plotted the light intensity at which they were grown versus the doubling time. So lower is faster, and you see there's a clear negative correlation that those which are growing very fast in the 2-hour range are also consuming a lot of photons to do so. So in itself, they won't increase the productivity, but they consume just more photons to achieve these higher rates. And the relevant point here is also that often these parameters are unfortunately not measured, and I really hope that people who study new strains look more quantitatively about what defines the growth properties. So none of these parameters I showed here are hard to measure. So these are quite classic phenomenological parameters. And if you measure them, you can really disentangle the contributions. So what leads to a higher growth rate, which you cannot if you just report the maximal growth rate of a new strain. So, oh, this new strain, it grows with 1.5 hour division time. So the second brief part will be about consequences for cultivation. And until now, we basically looked at a single cell. And here we now look at the productivity of a culture. And productivity is density times growth rate. So this is the definition of the productivity. I use the aerial productivity here. So this is gram dry weight per square meter per time. And the question is, how do these properties now translate to productivity? And we can look at this in a very simple model of the chemostat. And I have plotted here a heterotrophic chemostat. This is a textbook exercise you find in any chemical engineering book. You can calculate on a piece of paper. You have the dilution rate here of the chemostat. Then you have the plot, the curve. This is the productivity here. And then you have a peak close to the washout dilution rate of the chemostat. We can do now the same thing for the phototroph. And we get this plot. And this was actually also, to me, a bit surprising because it really looks as if it is flipped to the other side. So you have the same shape of the curve, but the peak is at low dilution rates here and fairly high densities. And the reason for this is that independent of the maximal growth rate of the strain for any strain, the quantum efficiency increases for lower growth rates. And the productivity is density times growth rate. So it makes more sense to have a higher density and a lower growth rate to achieve productivity than for the heterotroph. So for the phototrophic organism, really the density drives the growth rate, and it's a bit similar to the antenna truncation idea. So that is, and we already heard that also for the heterotrophs, of course, the high productivities we know are not because they are inherently better, it's because they have high densities in the culture. If you would grow E. coli or yeast at 1 gram per liter, you would have the same problems that with the algae. So the second take-home message is that the maximal productivity is achieved at lower growth rates, high culture density. Now, you can say there's this weird guy with the models. Do these curves mean anything? And there is not that much quantitative data, but there's a little bit, and I just show here one publication for Synecocystis 603 from Touloupakis a few years ago. And here is the model, and you see that they actually do a full chemostat cultivation. It's pretty similar. So here is the curve we get from this model. Now, as the last slide, I want to briefly mention on something on the antenna size truncation. Until now, I made this very simple model. This was all basically monotype models. But now we can also do more complicated models. And one of these classes, what we did, model classes, was the model where they can adjust the absorption per cell. And then we can really study what happens if we maximize the evolution of an individual cell that is selfish, tries to absorb as much as it can while the cell still improves its growth rate. So that's something that recovers the wild type then. And then we can look at the cells of which pigmentation would give the maximal productivity. And what happens is indeed that they would reduce the pigment content, so to maximize the productivity of the whole culture as the evolutionary objective instead of growth of a single organism, which is the actual objective in evolution. Drastically reduced pigments, denser culture, exactly as the antenna size truncation would predict, but there's no increase in productivity. And I also found this surprising because I was expecting an increase in productivity. And the reason why this is not in the model is because, and I think, and I would like to discuss this if anybody has an opinion on it, because there's one flaw in the reasoning of antenna truncation, and it's true the quantum efficiency increases. It's much better to have low light. The problem is the efficiency per photosystem decreases, so you don't use the photosystem to its full capacity and the electron transport chain. So you pay more for the photosystem. The cell, for the same kind of flux, absolute flux that it has, actually has to buy, to synthesize a lot more machinery. And this machinery costs, and this takes away the productivity. So you have two competing effects, higher quantum productivity, but also higher cost of cellular components. And in this model, they cancel each other. This then depends very strongly on the specifics of the strain, how these costs are. With this, I want to wrap up. So what we saw are high growth rates are not, so in particular strains with high maximal growth rates are not automatically more efficient or more productive. They might just be high light adapted, grow fast by consuming a lot of photons, but be actually less productive per photon. We don't know the trade-offs in these high, fast-growing strains very well. It's mainly because people have no incentive to actually measure these trade-offs. So how do they really behave in low light? What is the yield? What is the productivity per photon and so on? For phototrophs, density is really the driver of productivity. This holds also for heterotrophs, but for the phototrophs, in addition, you have the decrease in efficiency at high growth rates, irrespective of the maximal growth rate of the strain. Efficiency will always decrease for faster growth. And what I usually have in this kind of talk at the end is a demonstration how to experimentally implement this, but here we have something much better. We have the next talk, so we have a number of people involved, of course, from my group here, but also long-time collaborators, in particular Tomáš from Czech Republic, and also the funding. None of this is actually related to the phototrophic productivity, but they still pay me. And I want to then introduce the next talk, which will be specifically about how to implement these kind of high-density systems that would achieve then the best productivity that you can get with phototrophic organisms. And with this, I want to thank you and happy to take questions.
Thank you, Ralf. I completely agree what you were saying in terms of the high growth rate is unequal high efficiency of productivity. This is exactly what I said a couple of minutes ago. I completely agree. It's not about having a Ferrari that doubles every 20 minutes, the cell. It's about having high cell densities, and it's about controlling the metabolism for beta-carbon partitioning. That's what it's all about. That is what the bacteria community teaches us. We have just to look to what they are doing. So I completely agree. The problem is, however, and you mentioned that then you have to deal even with your great cell deck systems and wherever, when it comes to larger scale, with black cultures. And then we are talking about light penetration, dilution, which is a huge problem. So we have to talk about it. And in terms of the light antenna, I agree generally, yes, because most of the tests have been negative when people did it. But it's not, the solution in my mind is not a truncated antenna. That is not, because you downregulate everything without distinguishing between the different very specific subsystems. You have to be extremely careful. So you have to target single subunits of the system and target it very carefully and truncate it, not the whole antenna. That doesn't work. And that is, I think, one of the, we are just I have to say, we did CRISPR-Cas on all the single subs with Ben Henkamer in Australia together, and we are just testing them. And they are promising, much more promising than just taking the whole antenna or whatever. But I have no idea other than getting rid of the pigments, the green pigments. The green pigments are great, but in this case, they are a problem.
I mean, in general, I agree, and of course, this model is also without considering these pleiotropic effects that if you knock out something, you always affect a lot more things than you would wish for. But I still think that the general idea, what we do here, so what I try to show is that you still neglect in the intuitive consideration that if you operate at a low flux to the electron transport chain, which is the idea of antenna truncation, you reduce also the pay you get out of each photosystem, which diminishes your benefit. It might still be positive net, but there are two competing effects here.
Yeah, thanks, Ralf, for nice talk. I do agree that dense cultures are, of course, showing a more productivity, but truncated antenna. So we have a quite good result showing that if you go to multi-layer culture, where you have on the top the truncated antenna and then you have a wild type, you can see very nice increase in productivity, and also light to product conversion efficiency is much higher. So it can be somehow still involved.
First of all, I think the antenna, the idea behind it is completely correct. I mean, obviously you want deeper penetration, denser cultures. One thing I did not mention, which I should mention, is that the calculations I did are for biomass production. And in biomass production, the key factor is each component of the cell has basically to refinance itself. And then if you have a low flux, you have to pay more per component. If you do product formation, it's a bit different, but I think we can discuss this, so it's still an interesting topic.
Thank you for the excellent talk. I really enjoyed it. I think it's way better than the biochemical details. I like the mathematics. And I've noticed that you have taken into account the light intensity as a sole parameter affecting the productivity. Yep. But as we already know that there are some other potential inhibitors like the too much oxygen, too much carbon dioxide, yep, pH, temperature, and whatever. I wonder if you have an extended version of the monokinetics, including all these other inhibitors for the productivity.
I have a slightly extended with nitrogen, but it's of course true that in order to do this, you need specific media to actually achieve these high densities. They won't work with your standard lab medium. Okay. I mean, it won't sustain the density itself, and that's maybe something that Lars can talk about, which we also developed. I mean, for high density, you need a specific medium, and you need to make sure that oxygen does not accumulate and is removed. So all these things, of course, are part of it. They are not part of this model.
Okay, and then lastly, you've been working on the chemostat. I wonder if you ever tried the cell recycling and to see if it makes any difference in the productivity.
I did not. So here the chemostat is quite, because it's a simple mathematical model. So it's not really, it's also not a very complex model of a chemostat. So if you look at the chemical engineers, they make much more sophisticated models. Here it's more proof of concept kind of simulation.
Ralf, thank you. Very small. You cited a proteome work. It's actually a related question. In the chemostat, a lot of stuff is also changing at the same time. You have limiting nutrients at some point which affect the photosynthetic pigments. which are also directly related with the light harvesting and capturing. Can you still model that? I know this is a fairly complex issue too, but how does the limiting nutrient issue, the nutrients directly affecting the photosynthetic apparatus?
We can, I mean, these are then more complex models, and we do basically usually, so in the beginning I showed these more elaborate large-scale models, and there we really want to have crosstalk between nutrients, how can you substitute one, differences between nitrogen sources, that you can do, but then the model gets more complicated, and that's really here proof of concept kind of single curve. Of course, in general, for the algae field, the data is a bit lacking. If you compare to E. coli industrial biotechnology, you have really quantitative data about all this, whereas in the algae field, it's often a bit ad hoc. Somebody takes the Erlenmeyer flask and reports the yield per chlorophyll or so. That's not something that you can then really compare. So that's something that also the field maybe look more into, like quantitative experiments where you have real units, not relative to chlorophyll, which is good, I mean, for you, but if you then want to have more elaborate understanding, it's always good to have biophysical units. And by the way, because if somebody takes pictures, you can have the slides, of course, there's nothing secret, or just mail me or so.
Thank you for your valuable presentation, Ralf Steuer.